sheet that I started last time, but I had a few little supplemental things to add to it, just to go over root mean square and average RMS values. So if I want to get the average value for a periodic function, so the average value, the way I always think of average value is integral over interval. So I got these problems out of the textbook, the edition that I had when I took the class. And, rather than writing them up, I said, I'm just going to, take these pictures and give them to ChatGPT to have it give me the answer. So it gave me the wrong answer. And so then I told it what to do, and it gave me the wrong answer again. And then so I went and I got the solutions from the solutions manual. I'm like, I'm not going to do it that way. Because, you could. So it's integral over the interval. And so I could find the function that defines that line and then take the integral of it. But I know that the integral is the area of the curve. So I get one period, one complete period. So from start to then where I start over again. So that's a period, is a repeating segment. And then the integral is going to be the area under that curve, and that's a triangle. And so the area is going to be 1/2 times the base times the height, and the interval is 4 seconds. And the area is, I think this is voltage. And so that's volt seconds on top, because it's the height is volt and the base is seconds. So I get 0.75 volts is my average value. So now my root mean square is, this one is a little bit different. So if I take this one, I think I am going to have to write it out. It's 1 over the period times the integral from 0 to the period of the value of the function f of t squared dt. So I think I am going to have to get the function this time. And so the part from 2 to 4 is just going to be 0. So this is going to be the same as 1 over 4 times the integral from 0 to 2 of the linear part of this, which is a line through the origin with slope 3 over 2. So 3/2 t squared dt. The second half is just going to be 0, so that's not going to affect this part. And then I take the square root of the whole thing. So then this is the square root of 0.25 integral 0 to 2 of 1.5 squared is 2.25 t squared dt, or the square root of 0.25 2.25 over 3 t cubed from 0 to 2. Do any of you have a calculator?
I do.
Okay, so this would be 0.25 times 2.25 over 3 times 8. This would be 1 point something.
1.5.
After square root?
I don't know. 1.22.
1.22 volts. The next one to be, again, the average value won't be so bad, but the root mean square won't be as fun. So let's see. We would have one complete period going from 0 to 16. And if we look at our little line segments here, our line segments have slope 12 over 4, or slope 3. So they have slope 3, and then the first one, so if we think about where its y-intercept would be from 8 to 4, it goes down 12, so it'd go down 12 more. So this first little line segment would be, so we have I of t equals negative 12 from t greater than 0 and less than 4, and it equals 3t minus 24 from t greater than 4 but less than 8, and then from 8 to 12, let's see where its y-intercept would be. Looks like that would be at 36, right? Negative 36, down 12 more. So it would be 3t minus 36. And then the last segment is negative 12 from t between 12 and 16. So our average value is 1 over the interval, which is 16, times the integral. So the integral from 0 to 4 of minus 12 dt plus the integral from 4 to 8 of 3t minus 24 dt plus the integral from 8 to 12 of 3t minus 36 dt plus the integral from 12 to 16 of negative 12 dt. And then I am too lazy. So if I do, let's see, so I want 1/16 times the integral from 0 to, what was the first one, 4 of -12 plus the integral from 4 to 8 of 3x minus 24, or 3t minus 24. Plus the integral from 8 to 12. Did y'all know this calculator did this?
I have no idea.
Yeah.
I saw the button on that. That's crazy.
Yep. 3x. It messes up when you have like integrals to infinity. It doesn't do those well. And of course it doesn't do symbolic calculations, but just regular, like normal integrals like this, where I would make too many mistakes doing it by hand.
Maybe it takes a little time.
What's that?
Takes too much time.
Yeah. And -9, that's actually the right answer. So just did all that. And then if I wanted to do the root mean square, then the root mean square, I would do the square root of all of that, except I would go in and I would square each of the things in there, which I'm not going to go back and do, but that's, yeah. And then I'm certainly not going to do it by hand, but you would square them and do it out.
So is that all you can do for root mean square? It's just square the components?
You have square root on the outside, and then you square the inside of the integral. The 1/16 stays, it's under the square root, but it's not squared. So I would, the square root 1/16, and then I wonder if I can just put a squared right here. No. So I'll just change this to 144 because I know what 12 squared is. And then you would square each these linear terms. And then this last one needs to be 144. And 9.8 is the answer, 9.8 amps. Okay, and then for the ones that have function values, you do the same thing. So it would be what did the directions say? Okay, determine the average, okay. So, the thing with a sine or a cosine, if I'm looking for the average value, and this is one of the reasons we use root mean square, if I want the average value of sine or cosine, so here's sine, there's one complete period, and here's cosine, here's one complete period. What is the average value of this function going to be if I take the area under the curve, the total area under the curve, and then divide by 2 pi? What's that going to give me? 0. So the average value is going to be 0, and the average value of a constant is just going to be 2.5. The average value of 2.5 is just 2.5. The root mean square, though, is going to be different, because the root mean square, what that does is it squares it, and so it makes it all positive. So then when you find the area, you've got a positive number. And so you would take the let's see, so the period would be 2 pi over 60. Do I need that? I don't know if I need that. So it'd be 1 over t, and I'm going to take the square root of the whole thing. I'm doing the first one. And then the integral from 0 to t, whatever the period length is, of I don't actually need to do this. There's a reason why I don't need to do this. I could do it. So I could do it. So I could do 4 cosine 60t minus 30 degrees dt. I could do it, but I know that the root mean square for any sinusoid is the amplitude over the square root of 2. And so if I want the root mean square of 4 cosine 60t minus 36, or was it 30 degrees? 30 degrees. I don't have to do all this work. I know the root mean square is just going to be 4 over square root 2, which is something. So that's A. That's all I have to do for A. For B, the root mean square for a constant is just going to be a constant, so that's not going to change anything. C is the one where you have to do a little bit of work. So it's not a sinusoid because you have that 12 in there. So it's going to be the integral 1 over the period, the square root, 1 over the period, and then 0 to t of the first part, which is the 12, so square that, 144 dt, minus the integral from 0 to t of sorry, I should have done this first. 12 minus sine 2t plus 45. I'm actually not going to, I'm much, much too lazy. I'm not going to do all that. So just take my function, 12 minus sine 2t plus 45 degrees squared dt, and do that. If I were to do this on the calculator, I would want to change this 45 degrees to radians. What's really interesting about the way they do the sines and cosines, at least in electrical engineering, is this number is in radians, but this number is in degrees. And so if you want to actually get your calculator to do it, you want to change it to radians. So if we wanted to get the right answer, and then the period is going to be, if you remember way back when, the period is going to be 2 pi over 2 from this part right here. So it would, if you wanted to do this on the calculator, it'd be 1 over pi times the integral from 0 to pi of 12 minus, oops, I don't need that, sine 2t plus pi over 4 all squared dt. And someone brave can do that and see if the answer is actually 12.32, but I'm not that brave. But if you were going to try to do it by hand, you'd actually have to do this integral, and I'm not doing it. I took Calc 2, and I don't need to do it again. And see if it works. I need to change my calculator to radians as well. So 0 to pi, 12 minus sine 2x plus pi over 4, close parentheses, squared dx, square root of all that, in radians. And it's thinking, and it didn't get the right answer. Oh wait, yeah, it did. It actually got the right answer. How about that? So 12.32 volts. All right, so let's move on now and go back to the worksheet that we started last time, and let's talk a little bit more about power. I didn't do the QR code, did I? Let me do that. Any questions while I'm pulling up the QR code?
So the VM the amplitude of the sound wave.
Mm-hmm.
Then how do we figure that out on the non-sinusoidal, because the VRMS is the formula.
Right, so what's the question?
For a non-sinusoidal graph, how do we get the VM? Is that just like the highest point?
Yeah, but you can't use that formula for non-sinusoidal. So for non-sinusoidal, you have to do the square root of the function squared
For RMS.
for RMS. Right, but everything that y'all will be doing will be sinusoidal. And so the RMS is just going to be divided by the square root of 2. So it's the phasor, the amplitude divided by the square root of 2. Except, I don't know if like y'all have like a homework question or something or whatever that has a different kind of function that's not sinusoidal. Is there an example?
Yeah, he gives us a handout in class, and he just discussed it and said that we are never gonna use anything else sinusoidal.
Right, and that's what which is pretty much what I just said too. So it's good to know. What's that?
Then the quiz wasn't sinusoidal.
And then the quiz wasn't sinusoidal. Have y'all already had that quiz?
Yes, Friday.
Oh, okay. So that's okay. So is it a triangular waveform of some sort?
It's exponential.
Exponential.
Or like a period.
Okay. Would y'all like me to do one like that, or you think you got it? You understand? Yes, I see it. Yeah. There's something like that in the book that I can do if y'all would.
Yeah, I would love that.
Okay. Did y'all get the QR code?
Yeah, I got it.
What kind of voltage source could give you that kind of wave?
Decaying. Oh well, nothing that would be periodic. Well, okay, like a capacitor, a decaying capacitor, and then if you can somehow quickly charge it up again and then let it decay. I don't know how you would exactly do that, but that, like if you were continually pressing the flash on an old style camera, that those were capacitors. So it'd be something like that. So it's similar to this one, but perhaps a little easier because you have straight lines, maybe?
Yeah.
Bring it here.
I was just asking about that because I can get the RMS value really easy. It's just that the only power equations we have use VM. And he's asking us for power.
Oh. I see. Okay.
We
All right,
might
let
just
me-
do some examples
Yeah,
tomorrow.
yeah,
That's
yeah,
just-
yeah. I'll still go ahead and do this one. Okay, so let's say this was our function, except instead of looking like this, it looked like this. So I would have the integral, well, the square root of 1 over 2 times the integral from 0 to 1 of 1 minus e to the minus 2t squared dt, because this second part here is 0. And then to do that, if I had to show my work, I would do the the square root of 1/2 times the integral from 0 to 1 of 1 minus e to the minus 2t, 1 minus e to the minus 2t dt. So that's 1/2 integral. 1 times 1 is 1. 1 minus e to the minus 2t is minus e to the 2t, and then I've got 2 of them, so minus 2e to the minus 2t. And then e to the minus 2t times e to the minus 2t is plus e to the minus 4t dt from 0 to 1. And then that would be the square root of 1/2 times t minus 2e to the negative 2t over negative 2 plus e to the negative 4t over negative 4. From 0 to 1. Which would be the square root of 1/2 times 1 minus 2e to the negative 2 over negative 2 plus e to the negative 4 over negative 4 minus 0 plus 1 minus 1/4, and then that equals something. I'll just compute that. All right, so the next thing I was going to talk about is, if you look, I have a second handout there, that little green sheet. And could you bring me one too? And I found all these equations very handy when trying to compute the different types of power, and real power, apparent power, reactive power, complex power. And so if I have my complex power, which I think he writes with a squiggly, is 1/2 VI conjugate. That little star means conjugate. That means you change the sign of the imaginary part, or you change the sign of the angle if you have it as a phasor. The reason it's 1/2 is because these values, the phasor values, are the peak values, and the root mean square would be the peak value divided by the square root of 2. And so if you have divided by the square root of 2 and divided by the square root of 2, and you multiply those together, you get 1/2. And so that's the same as saying the voltage times the RMS voltage times the current RMS voltage conjugate, and that equals your average power plus J times your reactive power. And then you can see you've got your formulas for your average power is just what you would expect it to be, it's I squared R, where these are not the complex values. These are just the magnitudes. So I squared the RMS magnitude, that's the average power, and it also equals V RMS squared R over the magnitude of Z squared. So let's say I needed to compute the average power of something that was purely resistive. So if it's purely resistive, then the magnet, so like if I had 5 ohms here, and I've got my VRMS here, then Z is 5 ohms and R is 5 ohms. And so in this case, VRMS squared times R over the magnitude of Z, so the magnitude of Z is 5, is R squared. So this is VRMS squared over R, which is just our old-fashioned formula for power. So I would think if you needed to compute the average power for something that was purely resistive, you would find the RMS voltage and divide it by the resistance. Now, if I had something that was reactive, then I would have I squared RMS X, which also equals V squared RMS X over the magnitude of Z squared. Now, if my Z is a combination of resistive and reactive stuff, this is not going to be just the reactance, but if it's all inductive or capacitive, then you'll have the same sort of thing show up again. So I think I have an example of that. Let's see. Did y'all see one of these? I was going to do 820 or 821, unless y'all have one that you like better. Okay. I'm going to take a real quick look at the solution, make sure that I am not doing anything wrong, and then so I decided I was going to make a video on that one later. All right, so let's go back to, I think we left off at question 9. Calculate the current in this circuit, and also the amount of mechanical power in units of horsepower required to turn this alternator. Assume 100% efficiency. Okay. So we know that the voltage here is 480 volts AC, and our frequency is 60 hertz. So I'll do that one another day. So our voltage is 480, and you could say angle 0 if you wanted to get it, the whole phasor in there. Our frequency is 60 hertz, which means our angular frequency is 2 pi times 60, which is something that you'll see this number frequently, because 60 hertz is the frequency for AC. So it's 377 radians per second. And so we can find the current just like you did, for test 1. And how would we do that? Sure, it's just voltage over resistance. So the current is 480 over 3.4, which is 141.2 amps. Now, our apparent power is S equals IV. That's if we already have root mean square, which it doesn't say that we do, but we can assume that we do in this problem. And so we would take 141.2 times 480. So there's nothing weird going on here. And you get 677.64.7 watts. Does anyone know how horsepower and watts are related? In mechanical engineering, they always make you use all kinds of crazy units, but horsepower is about 746 watts. So this would be 90.9 horsepower. Okay, so nothing weird going on here. Now let's turn the page. And now we've got a inductor instead of a resistor. So I've got same setup, but now I've got a 9.02 millihenry inductor. So my voltage is still 480 angle 0. What is my impedance here? So 9.02 times 10 to the negative 3rd times 2 pi times 60 and J. And this turns out to be 3.4 angle 90 degrees. or 3.4, or J 3.4. So we've got the same magnitude as in the problem before. And what is our current? Still going to be V over Z. So it'll be 480 over 3.4 angle 90 degrees, which gets 1.41.18 angle negative 90 degrees. What is our real power, or our average power? Zero. And how'd you get that?
It's because I remember last time you said the power of an inductor was 0 because it gets up and down.
Yep. And so the reason why is our average power is I squared RMS times R. But what's R is 0. So even though our current is the same, our resistance is 0. So our average power, our real average power is 0. We do have reactive power if we wanted to find that, but that's not something that is useful. So you don't want to have that.
And how do you determine which power formula you can use?
That's a really good question. So it depends on the question that's being asked. So I tend to always use the complex ones that have both the real and the imaginary parts, and then just take the one that I need. So like I like to use this one, that the complex power is 1/2 V complex voltage, complex current conjugate. And then I know that that's going to equal P average plus JQ, and that way it's all in there. So that's usually what I do. Sometimes if I know I'm just looking for real average power, for instance, I know that all I need is I squared RMS R, and so I would just use that. So it kind of depends on if you're supposed to be looking for complex power or not. Like let me see if I have an example. So determine the complex power, apparent power, average power, absorbed, reactive power, and power factor, whether it's leading or lagging. Have y'all gotten there yet? Power factor? Okay, so we won't do that part yet. But let's take a look at, say, D. So we have V RMS is 240 angle 0 degrees. I RMS is 0.8 angle 50 degrees. And so we have them as complex, we have them as phasors, and they're given to us as RMS. So if I want to find the complex power, I'm just going to do V RMS, I RMS conjugate, which would be 240 angle 0 times 0.8 angle negative 50 degrees, which would be (192) angle negative 50 degrees, which then, if I needed to get the other kinds of power, what I would do, this is how I do it, to make sure I have the right answer before I go any further. Yeah. So this is the complex power, so that's VAR. And then what I do with that is I get that it's 123 minus J147 VAR. So that means my real average power is 123 watts, and my reactive power is minus 147 VA. So that's how I do it. I mean, the truth is you can use any of the formulas, you just have to be careful, and I find that I don't necessarily do it the same way other people do it, because I like complex numbers, and so I don't mind working with them, but a lot of people prefer not to, so they use the real numbers. Again, let me just make sure those are correct, 123 and negative 147. (123 negative 147), yep. Okay, so along those lines, this is the next one in the handout. If I had it has a lot of words in the handout that you don't really need all those words. Is this given as 4 kiloohms? Yeah, it has XC is 4 kiloohms, but we know that's a capacitor. That's got to be minus 4K or minus JK4 if we put it in complex, and 3 kiloohms here. So for this one, our impedance would be 3,000 minus J 4,000. And so we could get our current would be V over Z, which would be 0.6 plus J.8 milliamps. Just if you do 5 divided by 3,000 minus J 4,000 and convert it all. So then our complex power is going to be VI conjugate. Now, You have to be real careful because on this particular handout, they're not labeling them as RMS, but they mean for you to know that they're RMS. And so whenever you're not sure, you should always ask. So like if you have it on a test and it's not specific, you should ask. So this would be, our voltage would be 5 times the conjugate of our current, which would be 0.6 minus J.8. And that would get us 3 plus J, or 3 minus J4 milli VAR. What is the magnitude of the current? So here's our current. What's its magnitude? So like if I wanted to use the formula that has power is I squared R. So I want to use real average power is I squared R. That's not the complex power, that's the magnitude, complex current, that's the magnitude of the current. So what would that be? Yeah, so it's 1 milliamp, so 0.001 amp. So what is the real average power for the resistor?
Which is the current going to the
So it would be 0.001 squared times 3,000, which is 0.003 watts. That's this part right here. What is the reactive power for the capacitor? That one is I squared X, which would be 0.001 times negative 4,000, which is negative 0.004 VA. That's this part right here. So we found the total complex power, but now we're seeing how it's like divided up by the different components in there. Does anyone remember what our horsepower was? It was 90 horsepower, yeah. Okay. So, do one more problem. Let's take our same alternator. This is problem 12. Our same alternator. And we've got 480 volts at 60 hertz. And this time we have both a resistor and an inductor. So the same ones that we've been working with, and this was 3.4 ohms, and this was 9.02 millihenries, and we found that this made this one J 3.4 ohms. So our current, V equals IZ, our current is going to be 480 over 3.4 plus J 3.4 which is 99.82 angle negative 45 degrees. So our real average power is I squared R. Now when you write, so this is an instance where I'm just using, you said, how do I know which formula to use? I'm looking for average power. I've solved for the current. I have its magnitude right here. I've got the resistance right here, so I'm just going to use this one. I'm not going to go all the way and find the complex power and then get the real part out of it. So our average power would be 99.82 squared times 3.4, which is 33,877 watts, which if you change it to horsepower is 45.4 horsepower. And so we have half the horsepower that we had from the one before. And that's going to be all that I'm going to do today.
So if there was no resistance, is it the real or the average power would be zero?
The real and average mean the same thing.
Okay.
Yep. So yes. The answer is yes.
Okay.
They would be. The complex power would not be zero. But
Okay.
yeah.